All right, homework number 8 starts with exercise 29, and we're just doing part A. So part A says, find an equation of the tangent line to the graph at the given point. So in order to find the equation for the tangent line, I need a point, which I have, and then I need the slope at that point. So I need to find f prime of 1, and I'm going to use the alternate form of the limit definition of a derivative, because that gets me this answer a little bit faster. So that's the limit as x approaches 1 of f of x minus f of 1, which is 1, over x minus c, which is 1. And then we can't plug 1 in right now because we would get 0 over 0. So we can work on this a little bit. I see a radical in the top. So if I multiply by the conjugate, that might get me somewhere. So now this is the limit as x approaches 1 of x minus 1 over the quantity x minus 1 times the quantity squared of x plus 1. And then these x minus 1s can cancel, so you just have a 1 on top. So now when you plug 1 into this, you get 1 over square root of 1 plus 1. So f prime of 1 is equal to 1/2. So that's my slope. I have my point. So the tangent line equation is y minus 1 equals 1/2 times x minus 1. And that's our final solution for part A. All right, moving on to number 37. I thought this was one of the hardest problems, I think, in the homework. So this one we're kind of going backwards. This says, find an equation of the line that is tangent to the graph of f and parallel to the given line. So, but this time they don't give me a point of tangency, so I can't just say, oh, f prime of 1 or whatever. So the first thing I think to do is figure out what is the slope that we're trying to be parallel to. And so you can figure that out by rearranging things a little bit. Get this into slope-intercept form. So the slope that I want to be parallel is negative 1/2. And I need to figure out an f prime of x equation so that I can set it equal to negative 1/2 and then get my point of tangency. Because to find an equation of the line, remember I need slope, but I also need a point. And so it's the points that I don't have this. I have the slope, but I don't have the point yet. So, all right, so let's find f prime of x. To do that, we have to use the limit definition of a derivative, not the alternate form, because the alternate form that I used in the last problem is only when you're plugging a number in. If you're evaluating, and I'm not evaluating, can't figure that out yet. So this is going to be the limit as delta x approaches 0 of 1 over square root of x plus delta x minus 1 over square root of x. This is the difference quotient, all over delta x. Okay, now there are a few ways you can tackle this. This is not a simple thing to work on here because this is a complex fraction, but it also has these radicals in it. So I think I'm going to get rid of the complex fraction first, meaning I'm going to multiply by each of these denominators in the top and in the bottom. So that at least gets rid of the complex fraction piece of it. So we have the limit as delta x approaches 0 of, so this would just be radical x for the first part. And then here I'd get minus radical x plus delta x. And then that's all over. Remember, we don't usually actually distribute this stuff together. There's a delta x down here. We're multiplying by a radical x plus delta x, and we're still multiplying by a radical x. So there's nothing to distribute anyway down there. All right. You can always check, can you plug in 0 for delta x right now? But if you do that, you'll get 0 over 0. So this is still needs to be worked on because you get that indeterminate form. So let's work on the radicals by multiplying by the conjugate. See if that helps. The conjugate of the numerator, that is. Okay, so if we do that, sorry, my arrows here. If we do that, remember conjugates multiply nicely together. So we get the limit as delta x approaches 0 of radical x times radical x is x. This radical times this radical is minus the quantity x plus delta x. We just throw this all together down here. So there's a delta x. There's a radical x plus delta x. There's a radical x. And then multiplied by the conjugate, which I'm not going to multiply through actually. I'm just going to lump it all together here. The conjugate is in parentheses. Okay, so does this help at all? We need this delta x to cancel. So let's look around here. This would be minus x minus delta x. So x minus x cancels. Negative delta x over delta x. Those are going to cancel to negative 1. And then what if we try direct substitution from here? So plug in 0 for delta x. So it's negative 1 on top. There's a radical x here. There's another radical x. In the parentheses, there's radical x plus another radical x. So just keeping track of all this, this is 2 radical x. Radical x times radical x is x. Okay, so f prime of x. I finally got it down to negative 1 over, let's make this 2x radical x. Okay, so we have our f prime equation, and remember what we need to do? We're trying to find the equation of a line that's parallel to this line and tangent to this line. So now that I have the slope formula, that's what the derivative is, I can say, all right, set the slope formula equal to negative 1/2 and see what x makes that happen. We're basically figuring out where is the point of tangency? Where does that need to be? All right, so if negative 1 over 2x radical x is equal to negative 1/2, maybe you can just look at this and see that it's going to be x equals 1, but you can also kind of do some solving. You could say, okay, multiply this over to this side. X radical x, 2x radical x would have to equal 2, and divide things out. You could also make this x to the 3/2. So either way, you're going to get that x equals 1. All right. So then what is my point? I have my slope. I had the slope to begin with for the line. The point, the x coordinate's 1. What is f of 1? 1 over square root of 1 is 1. So the point that I'm working with is the point of tangency is 1, 1. So finally, the tangent line that's parallel to this line and tangent to this graph is y minus 1 equals negative 1/2 x minus 1. Like I said, that's a really complicated problem in my opinion, especially when we're not using derivative rules, when we're going through this long version of finding a derivative. Next week, this would be kind of an easy problem because we'll have a shortcut for how to get here. All right, next part. The graph of f is given. Select the graph of f prime. So 39 through 42, I drew a line here. These are the graphs of f. If we were to figure out their derivative, their tangent slopes, and plot the tangent slopes, which graph would that look like? Okay, so, and again, this could be kind of hard to wrap your brain around, but remember, derivative f prime is equal to the derivative, and that's equal to the tangent slopes graph. So when I do these, I kind of think of it like this. What is the tangent slope? Well, of a line, a linear function, the tangent slope formula is always just going to be whatever that slope is. If this slope is 1, that means that I should be looking for a graph where f prime is just equal to 1. So do we have a horizontal line? Yeah, so right here, horizontal line at 1. So the f prime graph for number 39 has to be graph B. And then if we go over to our parabola, so think about the slopes here. The tangent slopes are going to be really negative, but gradually getting to 0. So f prime is going to be something like, it's going to be negative, it's going to be getting to 0, and then positive, 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 maybe something like that. Okay, now I curved mine, but this is a quadratic, right? And again, we haven't talked about We haven't talked about these rules officially, but the derivative of a quadratic is actually linear. So the only, out of all these four choices, the only one that goes negative to positive is D. So you can process of eliminate like that. All right, for 41, or actually I might go to 42 because anytime I see linear segments, that's easy to pick out. This slope over here is -1, while this slope is +1. So the derivative graph should have a horizontal line at -1 and then switch to +1. So that is graph C. So by default, we have A for this one, but we can investigate here. The slopes are positive, and right here is a vertical tangent because you kind of have like a really steep slope and then it starts leveling out to 0. And here we have a really steep slope, really high number for f prime, and then it really dramatically starts decreasing towards 0. We'll practice this skill more. The more we talk about derivative rules, it'll get easier when you can match things up with the shortcuts. Describe the x values at which f is differentiable. So I'm going to start with where it's not differentiable. So there's a discontinuity at x equals 3 right here. So this graph is not differentiable there. But otherwise, it's differentiable from -infinity up to 3, and then from 3 to infinity. And for 84, we have two sharp turns. So not differentiable at plus or minus 3, which means it's differentiable everywhere else. So -infinity to -3, -3 to 3, and 3 to infinity. Remember, differentiable means has derivative. You could find a tangent slope at that point. All right, and then these last three here. So x plus 4 to the 2/3 is this cusp shape here. So not differentiable at -4. Otherwise, it's differentiable everywhere else. There are vertical asymptotes at plus and -2. Otherwise, we have a smooth curve on each branch. So x not equal to plus or -2. You're basically describing each branch here. And then for this last one, differentiable everywhere except, I want to go back to this graph here. At x equals 0 for number 41, see how there's a vertical asymptote on the f prime graph? That's because there's that vertical tangent at exactly the starting point. So same idea here. There is a vertical tangent right here, and then the graph will exist and be like really steep slopes and then going out to 0. So not differentiable at 1, but anything after 1, we're differentiable. Okay, in these questions, find the derivatives from the left and from the right at 1, if they exist. Is the function differentiable at 1? Now, I'll admit on my answer key, I did not go into the full limit definition of this. You can sketch these graphs as well and kind of try to decide what's going on. Are there sharp turns or not? So this graph, I know at 1, there's a sharp turn. So I know it's not differentiable. But if I'm supposed to find the derivatives, I'm going to say f prime of x. Remember, this graph, this absolute value graph, derivatives are just what are the tangent slopes at each point. So the tangent slopes will be -1 if you're to the left, if you're at x is less than 1, and it'll be +1 if you're to the right of 1. And because this is not a continuous function, if f prime is not continuous, then, or doesn't exist at a certain point, then f of x is not differentiable. So f of x is not differentiable at x equals 1. And I could say because f prime of x is not continuous at x equals 1. If I were to graph this, it's one of those piecewise functions. So I can do that for each one. So for 96, I can think of, okay, what is f prime of x? So this is a linear segment, right? So the slope is 1 everywhere for x values. So the derivative is 1 for x values that are less than or equal to 1. And then what about x squared? So again, if you go through the limit process, the limit as delta x approaches 0, of x plus delta x squared. I'll set it up, but I'm not actually going to do it just to save time. If we go through all of this, we should get the final answer is 2x. Because, again, we're going to learn shortcuts next week. The derivative of x squared is 2x. Okay, so if that's the case, that's for x greater than 1. And again, is this a continuous graph or not? When you plug in 1, you get 1. So that's like here. And then when you plug in 1 to 2x, you get 2. And then you go off that way. So that graph, again, is not continuous. So same thing. F of x is not differentiable at x equals 1. And that's because f prime of x is not continuous. All right. 97. This is our last problem. Determine whether the function is differentiable at x equals 2. So differentiable is, again, we want to think about the derivative graph. Or you could graph these two things and say, like, well, I don't know, is this a smooth curve or not? That's kind of hard to tell. So I would go back to the idea of the derivative. And again, similarly with x squared, when we took the derivative, if you do the limit definition, if you take the derivative of x squared, the limit definition of a derivative, you're going to get 2x. It's the same thing with x squared plus 1. You're still going to get 2x. So I know I'm kind of skipping steps, but I'm running out of time for my video here. So the f of x is 2x if you are less than or equal to 2. And then this is a linear function. Its slope is 4, so I know the derivative is 4. X is greater than 2. And so is this derivative graph continuous or not? That's all we're looking for, is a discontinuity. So here it's continuous, right? Because when I plug in 2, I get 4. And so this is like to the left, we have like something like this. And then for the rest of the graph, we stay at 4. The idea is not that, oh, there's a sharp turn in the derivative graph. That's okay. It's just, is the derivative graph continuous? Yes. So f of x is continuous. Is differentiable at x equals 2. And that's because f prime of x is continuous at x equals 2. All right, it's kind of confusing. I think these last problems and that 37, those are pretty tricky problems. So this is a little bit hard to wrap your brain around. Feel free to come in and ask questions during office hours if you have any.